All right. So today we're going to be doing a review of Exam 3 materials. And here are some things on the screen that you need to keep in mind. So for mechanisms, there's going to be 3 mechanisms from this section alone. So there's going to be other mechanisms from the other sections as well. But we'll talk about some of those in a second. Or go back on your notes and check those out. So the first thing I want to talk about is classification. So we're going to be talking about classifying ketols and acetols, and then whether or not they're hemi. So how it works is that the ketols are the ones that have the key here. Just a second. So first you have to look at the carbon that is going to have 4 things attached off of it, right? And so those 4 things can either be, sometimes you have something like this, and then sometimes you have an OH. You also might have hydrogens to take into account, and then you usually have 1 more carbon. And so 1 or 2 more carbons. So if you have 2 carbons that attach off of something, it is called a ketol. Okay, so so something that has 2 carbons on it is a ketol, right? And then from there, to figure out whether or not it's a hemiketol, what you have to do is think about if there's no hydrogen. Okay, so if there is a hydrogen, then it's called a wait a second. No, if there I'm getting a little confused because I'm looking at your thing, Julie Dye, and this is just really confusing me because I've never really seen it before. Okay, well, I guess from here you're either gonna have alcohols or you're gonna have esters or ethers. So if you have 2 esters, then you can call this a full-blown ketone, and if you have an ester and an OH, then that's a hemi. Similarly with your acetols are just gonna have for the bottom part, they're gonna have a carbon and a hydrogen, so that's what defines them as acetols. And then for them to be same as above, for them to be regular acetols, they just have to have 2 ethers, and then if they have an ether and an alcohol, then we call them hemi-acetols. So that's just how to name them, and you're going to have to do that on the exam for sure. There's also a chart that a lot of people have found useful that JD sent to the group. So yeah, you could use that as well if that helps you. Okay, so next, I want to go to some Witting reactions. So Witting reactions are definitely going to be on the exam. And the way that they work is they take a carbonyl, and so we could have any carbonyl that looks like this, for example, and we're going to react that with something that is attached to so we could have like this, for example. And what this, and there's going to be a positive charge here. And so all this does is you simply take the carbonyl and you erase that oxygen, and then you just attach on the portion of the carbon that was attached to the O3P or the elide, right? And so this reaction does it can also involve some other things, which we'll talk about in a second. Do you guys think the nitrogen ones also fall under the Witting reaction umbrella? I think maybe. So maybe they're technically considered something else. But you can also do your Wittig reactions with a nitrogen. Or actually, no. Never mind. We'll talk about that in a second. So this is the basics of your Wittig reactions. So all you need is you need a carbonyl, and then you also need something that is an ylide. And so one of the questions you're going to get on the exam is you're going to be asked to identify an ylide and a carbonyl group for something. So you have to go backwards, essentially. You'll be asked to find the two products that form something. And so, for example, if I gave you this question, and in this question, I'm asking you, what's the ylide, and then what's the other one that had a carbonyl? And so what you have to do is you have to figure out, okay, so, and there's lots of different options for this, but you just have to draw one of them. So you could do it on either side. You could make this side your ylide, and so to make this your ylide, you would just put like that, and then you would, on the other side, you would have your carbonyl that goes like this. Or you could switch it around as well. That would probably be okay. So all you do is the carbonyl will be on this side. Oh no, that's incorrect. Carbonyl would be like this. It would actually be an aldehyde. And then, and this is an aldehyde too. And then the ylide would be like that. So either one is totally possible. You just have to be able to draw them correctly. And then your ylides can also, a similar one can occur with a nitrogen, and I guess I'll just talk about that now real quick. So with nitrogens, if we were to get given the same exact problem as before as well, so let's say that there was something like this, and it reacted with a carbonyl, was like this. Okay, so what you would have to do in this case is you would have to like it's not really a Wittig reaction because it doesn't include an ylide, but it's kind of similar. So I'm just putting it here. But like what you have to do is you have to redraw the part that has the carbonyl on it. And then you can draw your double bond here, and then you can draw the nitrogen. And then from there, just attach what was on nitrogen in the way of carbons. But since this one has broken octet because nitrogen only wants to be attached to 3 things, what you have to do is you have to rearrange one of these double bonds and make it go down, okay? Because this is not going to work. So all your answer is going to be is a rearranged double bond, and then your nitrogen is going to be here, okay? So this would be your answer. But this is because your nitrogen is secondary, and I should change that because that has to have an NH. If your nitrogen was primary, then you would be able to keep it. So if I had something that was like this, I don't know, and I reacted that with the same thing as above, in this case, when you're writing your answer and you draw the original carbonyl, and then all you do is erase the oxygen, put the nitrogen in its place, and then draw the remaining carbon structure, you'll see that the nitrogen has maintained octet, so there's no need to rearrange it. So that's how you work with your nitrogens. Okay. And then also, here's an interesting one. It doesn't really necessarily need to be like that all the time. Here's a cool one where what's reacting is so just to challenge a little bit. So this reacting with this, all you have to do, it looks a little bit more complicated, but the answer is pretty straightforward. Just do the exact same process that I showed before, because this is the same question. It involves a carbonyl and then a nitrogen in some form. So all you have to do is keep the same exact process we just talked about, draw the carbonyl portion, and then all you have to do is erase those oxygens, put nitrogens in their place, and then draw the remaining carbon structure, right? And this is really, really ugly, but you get the point that I'm talking about. So this is the answer. So really, it's most important to figure out, is your nitrogen primary or secondary? Of course, in this case, it's primary because it's only attached to one carbon. And so when it's primary, there's no need for rearrangement. But when it's secondary, you should never, ever, ever draw this right here where it has broken octet. Okay, that's all I want to say about that. So let's see what's next. Okay, beta ketoacids. So for beta ketoacids, this is something that confuses a lot of people, but beta ketoacids are actually pretty simple. All you have to do is identify an acid and then look and see if there's a beta keto to that. So, for example, here is a molecule, and we have to figure out, is it a beta keto acid? Because beta keto acids can undergo very special reactions, as we know. And so when we look at it, here's our acid, right? And so this would be considered the alpha carbon, right? And this would be considered the beta carbon. So no, this is not a beta keto acid. However, let's find another one. Because if you draw this structure out right here, it goes, right? So this is the alpha one. You wouldn't consider this one alpha. It's, it's actually involved in the acid itself. So it can't be the alpha carbon. So here's another one. And in this case, we count alpha, beta, and there is a ketone in the beta position. So perfect. This is a beta keto acid, okay? So that's the very simple method, and that's all you have to do. Next, and I'll talk about the reactions that actually happen with beta keto acid in a second, or in another portion. So acetol and ketol formation. How does this even happen? So we've talked about the structure of acetols and ketols, but we also need to talk about how they form and then how they break, how they can be hydrolyzed. So for formation of these, all you're doing is you are attacking, okay, you're attacking a carbonyl with an alcohol, okay? All it takes is a carbonyl and an alcohol, or two alcohols. It really depends. So if I reacted this with one alcohol, right, what I would get is I would get the same carbonyl structure, right? But what you have to do is break up that carbonyl into two OHs. And one of those OHs is reacting with this OH, and we all know that that forms an ether. So what it really becomes is this. And this would be considered a hemiketol. Ketol because it has two carbons, and hemi because it's only partially turned into an ether, right? After that, we can take this same thing and we can react it with one more alcohol. That's really up to you and your retrosynthesis or whatever you need. But it could be reacted with another alcohol, and all that happens is that this alcohol reacts with this alcohol, and again, another ether will form. So this one is a full-blown ketol. Okay. And then this process, though, can be easily, very, very easily reversed. All you have to do is use acid, I believe, to reverse it. Yes, I think it's acid. yeah, all you have to do is like use acid to break it apart again. And so just be careful of that. Anytime you see something that looks like this and it's reacting with acid, all you have to do is reduce it back down to hydrolyze it back to its ketone and the two alcohols. A very important use for this is capping something. So when you're doing a retrosynthesis, you might find that you need to cap something. And all that is you take your carbonyl. Let's say that I have 2 carbonyls on this molecule. And I want to make okay, I want to make this. So all I have to do in this case is I just have to cap one of them first. So what that is you take this, and it has 2 OHs already on it, and maybe H3O plus, and then all you have to do is we would take this one and cap it, so it would end up like this. So then from there we can do our Witting reaction, and that's great because with this Witting reaction we'll make sure that only one of them happens to be processed. So it will include that, 2 carbons in it, right? So then from there we have this, which is correct, what we want, but we still have a capped ketone, so all we have to do is H3O plus to get that removed. Okay, so that's the use of capping. Make sure to use it so that you can make your reactions like perfectly done and very, very neat and stuff. Okay, what's next? Okay, so for amides and stuff, there's something else that you can do, which I believe is an imide or an imide. I think it's like this or something like this. And what they are is they are carbonyls that look like esters, except that there's a nitrogen next to them. And so how are these formed? These are formed exactly the same way that esters are formed. All you need is an OH and a nitrogen. So how can this be formed? It can be formed from, like we'll take this example, it can be formed from an acid. It has to be an acid, right? Because we need this carbonyl in this position, and then we also need the oxygen to react with the nitrogen. And then it would have a nitrogen, and that nitrogen would have to have, it could have either a positive charge or not, and we'll go into that in a second. So let's say that it's NH3 with a positive charge. So that one was with an acid. And so you guys did take this exam recently, so I'm assuming you'll remember most of this. If it has an acid, if it's using an acid to form, then make sure that your nitrogen has a positive charge right here. And so that's how you can form the imide. The other way is with maybe not an acid. I don't really know of a way of, I'm trying to find an example like that, so I'm not like just saying something random. But I think that he always tends to use bases, really. Yeah, he really tends to use bases. So just make sure that this, like if you're working on it backwards, make sure that this has a positive charge. And then how do we break those apart? So we break them apart again just with acid. So forming them and unforming them is exactly the same, just use acid. So that's why it's kind of like, you can think of it like many of the other reactions in this section. They just have they all simply have acid somehow that makes them go back and forth. Okay. And that's really the end of that. So now I'm just going to go through a series of reactions, random reactions that you need to know. So the first one is, I forget the name, but this is really, really, really important. This is the one where you are taking a ketone and you're changing it to an ester. But the example is like this. You use this, and then all you have to do is use, for example, CH3CO3H, which is the one that normally with a double bond would give us an epoxy. But in this case, what it does is it inserts an oxygen in the position that is closest, or in the position that has the least hydrogens on it. So that's kind of what it looks like. More often you'll see this is like really like the most common use for it when you're doing retrosynthesis especially. So again, CH3CO3H, and what that'll do is just put that oxygen in there. Okay. So you just take the side that has the least number of hydrogens and you insert an oxygen there. And it specifically has to go to that side, so watch out for that. And then there is the reaction for the Whitting-like reaction, but with nitrogens. To remind you though, that when you have your oxygens like this and you're reacting it with the nitrogen, it doesn't necessarily need to be attached to carbons. It could be attached to like an OH, for example. Because this is the example I'm looking at right now. And so all you have to do is just the exact same thing. Okay? Or you could probably more conventionally write it like this. That's just so that you don't get surprised when you see that. Okay, and right now I'm going through like every single problem from your practice exam 3. So, next one. So this one, it has an acid, and it's reacting with first LAH. What do we know of LAH? It can attack an acid, and it can change it to what do you call it? Like this. I'll show in a second. Let's change this to a bond line format so we can look at it more accurately. So all it's going to do is it's going to change the, it's going to take an H minus, it's going to attack here, it's going to go up, come down, whatever. And then this has to break. Wait, does that break? Yeah, either way. So then what you get is you get this from the LAH product, and then after that it has PBr3, and so that one everyone knows by now. PBr3 just takes that OH and changes it to a Br, and that's a sign that really, like, once you change it to Br, you can do so many things with it. From there, you can it says KCN. So KCN reacting with a Br is just going to replace the Br with a CN. So take that Br, erase it, that's now a CN. And then finally it's reacting with heat and H3O+. And so all that's going to do is, and this is a really, really crazy reaction that a lot of people forget about. A lot. But it changes, what it does is it's going to change that into CO2H, an acid. And the way that I think about it is you've already set up the process by having a C here, right? So when you add this additional C, this C, all it has to do is take on an oxygen here and an oxygen here. Those oxygens are readily available in the water or in the acid. So, and the water that's surrounding it. So for that reason, it's really not that outrageous of a mechanism. If you think about it, all you're doing is adding 2 oxygens to an existing C. But yeah, that's a really important one. Next, we have another one. So this one is cyclic, and it's reacting with LAH. And this one is really, really simple. Everyone should be familiar with this. So LAH, it's going to, you have a hydrogen, H minus, it'll attack, that'll go up, come down, break off. So that's going to give us this, right? And then, because it's LAH, you can always assume that it's excess. Then another hydrogen is going to come along, attack. This is going to go up, whatever, grab a hydrogen. So our end product is going to look like this. OH and OH. Okay? Please always, always, always fully do your LHs. You can always assume that it's excess. This is time and time again from all of our practice examples. It's going to be excess. Okay. So in this next one, and this one's very interesting for sure. And you will face a lot of really interesting shapes on this final, and also on your last exam you did. Because this is, I think of it like the equivalent of in Orgo 1 when you guys did Diels-Alder's reactions, I think. So it included a diene and a dienophile. And with that reaction, you can make some really crazy shapes. So this is the portion of the class where you get to that kind of stuff. So for the next question, okay, for the next question, this is what you have. And this is reacting with H3O+. So when you think about H3O+ and a carbonyl, this should be like, wow, you immediately know what it is. And what it is that it's just gonna form a ketol. It's a ketol formation. Because that's what happens when you have alcohols reacting with a ketone. So in terms of shape with this one, the ketone is going to break into 2 OHs, essentially, going to each side, right? That's the way that I would think about it first. And then after that, it's a simple matter of forming the necessary ethers. So I'm just going to go ahead and erase this, erase that, put an O there, attach it, and then same thing on the left side. And that's the answer. So it's fairly simple if you break it down. Just remember the basics. If you look at a question and you're a little bit confused, just draw like a really simple version of the question on the side, and that'll help you remember. Just do the basic steps. Don't do anything fancy or extra. There's no need to go overboard. So for the next one, this is something that we've already talked about. Okay. So in this reaction, it's that Whitting-like reaction. I still don't really know the name of it. But with this, all that happens is that you can redraw it. I'm going to turn my ketone so that it's facing upwards because that's where it's going to react, right? And then I'll just draw the remaining things that are involved. And then on the other side, I'll just do the same thing. Oops. Yeah. So from here, all you have to do is the process that we talked about. Erase the O, put an N in that position. That is the N itself, right? And then, does it fit the, does it work in terms of octet? Yes. it does work because your nitrogen was actually primary. It's only attached to one carbon. So for that reason, it does totally work and you don't need to do any rearrangements or anything. Okay, next, again, a very similar question. Actually, I might have done this one, but just in case. Okay, so for this one, stick to the process. I'm drawing my ketone again. Erase that O, put the nitrogen in its place, and then draw the remaining things. Now in this case, this has broken its octet. So erase one of those double bonds and rearrange it. Obviously, it cannot go to the left. And anytime you're rearranging double bonds, stick to the rules. Zaitsev's rule, you want the most substituents possible. But obviously, you can't go to the left, even though it would have more substituents, because that would break the octet of that carbon. That would be really, really messy. So just keep all the regular rules of, like, for example, when you're doing elimination. Every time you form a double bond, think through the regular rules you've known for almost, for 2 semesters now. Okay, next. Primary OH reacts with PCC and then reacts with 2 moles of a alcohol. So I think I know where this is going, the 2 moles of alcohol. So PCC all it does is turn that into a ketone, into an aldehyde, right? So aldehyde goes here. Then you just have to attach your 2 oxygens. So the answer is a acetol or acetol. And then there is lots of other stuff. Okay, here's a really good one because this one forces you to okay, so we're reacting this with NaBH4, which, as you remember, is the LAH equivalent, but it cannot react on as many things as LAH can. And so you should definitely review that information from exam board or two, wherever it is, to brush up on that. So the first step is that it's reacting with NaBH4, and NaBH4 can only react with ketones or aldehydes. It cannot react with acids or esters like LAH can, right? And so all that does is it takes an H- and attacks the carbonyl with it. And it attacks this carbonyl specifically. It cannot attack the other one because that one is an acid. So this is going to form, and I might be off on the carbons, but that's not really the point here. It's going to turn that to an oxygen. At this point, when you put it in an acidic solution, all that's going to happen is that we're going to end up forming an ester, right, between those 2 alcohols. So this is a cyclicization question, right? And if I want to figure out, like, how many members are going to be in this ring, because I don't want to do that whole thing where people, like, shape it into a circle slowly. So one of the members is definitely going to be that oxygen that happens between the 2 of them. So, but make sure to count one of them and not the other one, right? Because there's only going to be 1 oxygen that forms between the 2 of them reacting. 3, 4, 5, and 6. So this is your simple hexane shape. But just put an oxygen in there. So that oxygen has a carbonyl to one side, and to the other side, right next to it, will have 1 methyl. So that's the answer. Okay, I'm going to do a little bit of skipping just because there's a lot of repetition here. Here is a hydrolysis using a base, and that's really, really important because it does differ from a hydrolysis with an acid. So Okay, so this is what we're working with, and this is reacting with an OH minus, again, a base. Now, if it was an acid, we would just break it up very simply into its parts. But since it's a base, you do the same thing, right? So this must have come from an acid and also an alcohol. But all you have to do is make sure that this acid is not an acid, it's actually the base version. So give it an O minus. That's it. Because obviously it wouldn't last 2 seconds as an acid in a very basic solution. It would lose its hydrogen immediately, right? Because you have to remember, even though we call this a strong acid in orgo, it is not a strong acid. If you remember from Gen Chem, the strong acids, there's a list of 7 of them, I believe. And yes, this is definitely not a strong acid. In the end of the day, this is a way stronger base, so it will take that hydrogen immediately, and we'll be left with this. In fact, I think maybe you would also be left, this one too, should also have a negative charge. All right. So this is what differs between using this and an acid to hydrolyze them. And in terms of doing this, you actually only need to know where's the list? You only need to know the acid one, I believe. Yes, hydrolysis of an ester by acid. You do not need to know the base mechanism, although it's just the same thing, but instead it uses, it takes away the hydrogen at the end. So if this had been with an acid instead, then all we would do is do the exact same thing, but we would leave it neutral. So that would maintain its OH here. Okay. Okay. How do you form an ylide, right? Because sometimes you're doing a retrosynthesis and you need to form an ylide. Here's a good question to help you figure that out. So in this question, we have it reacting, this chemical reacting with, firstly, PTH3, and secondly, N-BULI, NBULI. And so what happens at the end of this is, so for the first part, what happens is that I believe this is the process. This gets turned into phenol free, whatever, an ylide. But it's actually not quite an ylide because the second part is when this becomes a positive charge. But then this spontaneously undergoes Witting. So I'm going to count it up to see how many members are going to be in my circle, right? And we have to remember this oxygen is no longer going to be a member of the circle. So it's going to be 1, 2, 3, and 4. 4 members of my ring. So I'm going to draw a 4-membered ring. And then I'm just going to include a double bond here to signify that this is where everything happened. And then all I have to remember is that on the other side of the ketone, there was an ethyl, right? So that's the answer. So there are a few other reactions from this exam. I would recommend looking at your old lists. I'm sure that you have them in your notes and stuff. There's lots of random things you need to know. And we also just took this exam, so it should be pretty fresh. But yeah, the formation of the ylide is an important one. Okay, let's do a couple of retrosynthesis. We have about 30 minutes left, so we'll do some retrosynthesis, a little bit of NMR, and then we'll be done for today. So retrosynthesis. I'm choosing the most crazy retrosynthesis that is in this exam. And it is, actually, I don't know if it's so crazy, but anyways, looks like no one else got it really right, so. Okay. So here, all we have to do is, well, actually, this is a little bit complicated. So we know that we're starting off with one benzene ring, so we only have to add two more, right? Interestingly. And we also have this carbon already, the central carbon right there. We already have it. So what do we need to add? We need to add the oxygen and three phenols. So how are we going to do that? This should ring a bell, of course, for you that of what happens when, wow, this retrosynthesis is crazy. Okay. I have an idea here, and I just want to try it out because the answer key is just not what I would think to do. Or actually, yeah, no, I see it. Okay. All right, so what we have to do here is we need to think through how we're going to end up in a situation where two phenols can attack and we're left with an OH. So the only way for that to really work is if you have a benzene that has like a carbonyl with an ester on it, or at least something that can break off, maybe a Cl, I don't know, at least something that can break off, because when the first phenol attacks, we're going to need to break something off, and then when the second phenol attacks, that's when it becomes an OH, right? And so the reason you can't just have a simple Grignard that's only an aldehyde is because if you had an aldehyde, you would only be able to attach one phenol to it. And then it would be, you know, stuck in this position with only two phenols on it. So for that reason, we have to make sure we first get an ester there. How are we going to get an ester there? So getting an ester there is a little bit complicated, but there is a kind of simple way. So if you use KMNO4, KMNO4 takes any available positions and turns them into and adds onto them CO2H, which is just an acid. And then from there, you can turn your acid to an ester pretty easily, am I right? So all you have to do, because let me draw this out in a bond line structure so that you can see it more clearly. No, wait. Sorry. So all you have to do is react with alcohol, right? And so when you react it with an alcohol, it immediately becomes our desired ester. And then from there, it's actually a very simple reaction. All you want to do is you want to attack the carbonyl, with a Grignard type of reaction. We want to form a Grignard reaction. So all it's going to be is we're going to attack this with 2 moles of a phenol that has MgBr on it. And also, we're just going to need our hydrogen as well, our acid as well. And that should give us the desired product. Okay. So that's one retrosynthesis. I'm going to choose one more. Here's a good one that takes into account some of the other things we've learned. So this one has a methyl off of it, and it has to become the same thing, but on the other side, and that is para to it, it has NH2. Oh, this is not very clear, NH2. For this, first we have to be able to add something in the para position. If you think about CH2, it is an alkyl group, And alkyl groups are activating and they are para-directing, so we honestly don't have to do anything more. All we have to do is react this with, so we can add probably a Br is the most common thing to do across from it. So we could just do Br2 and FeBr3. FeBr3. This is exam 1. And all that's going to do is add in the para position a Br. From there, we need to figure out how to turn it into a, because how do we get a nitrogen in that position? All we have to do is have an OH. An OH and a nitrogen will react, okay? And so in order to get an OH in that position, that is clearly an acid, and there's a few ways of getting an acid. There is the CN method, there is the Grignard method. Let's do the Grignard method first because that's the one shown in the answer key. So for the Grignard method, you're just going to need to include your MgEt2O. And that's going to turn that into something that's ready for a Grignard. And then at that point, all we have to do is CO2. And that'll turn it into an acid. Or, yeah. Okay. And then finally, all we have to do is react it with NH3. Okay. Oh. Actually. First, we need to turn it into a Cl. SOCl2. And then finally, NH3. Oops, this is wrong. At this point, it is Cl, and then NH3. Okay. So for this one, it just takes into account some of the stuff from exam 1 with para, ortho, meta, activating, deactivating, etc. Also, exam 1 or exam 2, creating an acid. And the other way of creating an acid would be to change this into, at this point when it's a Br, you could change it to a CN by just putting like KCN or something, and that'll give you a CN in the position where the Br had been. And then from there, it's just heat, I believe. Maybe acid. I'm not sure on that one, but something like that. And that just turns into a acid for you. So CO3H. Okay? Or O2, sorry. Yeah. So that's another option. Finally, let us review a little bit about NMR for these kinds of things. So here's a really good question that is pretty much something that we all need to review a little bit. So this question has 6 doublet, a 3 triplet, a 1 multiplet, a 2 doublet, and a 2 quartet. Or quintet. I always can't remember that one. But I think it's a quartet. So, and then the formula is C7H14O2. C7H14. That means that it has 1 degree of unsaturation. And so we know that there's going to be a double bond there, most likely involving one of those one of those oxygens. We also know that the other one is probably going to be an ester because there's no 1H singlet that could indicate an OH. So we know that we're dealing with an ester here. Let's start from the 6 doublet. So a 6 doublet it just looks like this. We have 3 hydrogens from each one of these, so that's a 6 doublet. And it's a doublet because adjacent to that there's only 1 hydrogen. And as you know, you add 1, so that's a doublet. So this here, it must be the multiplet, right? So here I'm just going to go ahead and I'm going to label them A, B, C, D, and E. So these are clearly going to be A together. This arrow right here is pointing to C because it's a 1 multiplet. And it's the only one option there, so that's how we know that. And then continuing off that, I think we don't really have much evidence to go forward from there. So I'm going to start from the 3 triplet end as well. So for the 3 triplet, we know that it looks like this. There's 3 hydrogens here, and there must be 2 hydrogens here. So going forward to label that, this is B, and then we have 2 options for the 2. It can either be C or D, but clearly it can't be D because it's already a quartet, so it's C. And that means that there must be no hydrogens there. So looking back real quick at our formula, how many carbons do we have? We have 1, 2, 3, 4, and 5. So we need 2 more carbons. So this could be, and I'm gonna put it in. So this could be the beginning of where our ester starts, right? And then that would be the continuation of our ester. And then let's see, 1 more. So it could be like this, right? Because we need 1 more carbon in there. So putting all this together, we haven't dealt with this one. This one is a 2, but it must be a 2 doublet because it is adjacent to only 1 hydrogen. So perfect. So I'm just going to relabel these again in red. So A, this is C, and then this one is the 2 doublets, that's D. And that accounts for all of our hydrogens. Now, the only thing is that there was nothing like this ester could be facing either way. So to figure out which way it's facing, all you do is look at the thing that's most far downstream, which is the 2 quartet. The 2 quartet is C, right? And so C, therefore, must be the one that is most closely associated with an oxygen, i.e., this is the correct orientation for this. Okay? And if you don't remember that stuff, you can talk to me or you can try to review it and figure out what I'm talking about. But essentially, because it's so far downstream, we know that it's very closely associated with a carbon, and that means that the oxygen is that the ester, the ether, is facing this side, not the carbonyl. Okay. So let's do. Actually, we've kind of come to the end. Do you guys have any questions? Those of you who are here. Any questions about anything? Because we've just come to the end of pretty much reviewing for exam 3. No questions? Okay. Ooh, oops, looks like I missed your question about the number of carbons in a Witting reagent. Look for the last time I used the Witting.
It was for like a synthesis type question, or what 2 pieces of this makes that?
Oh, okay. I think I might.
It's that one, that last one. That one with the protecting group.
Oh, okay. Oh yeah, I didn't realize that one was Witting as well. Are there enough carbons? Oh yeah, I think I might have mentioned that I lost track a little bit of carbons. I'm not sure. But what are you talking about specifically?
In that Wittig reagent that's in the middle, there are
Oh,
2
yeah.
carbons,
Yes, I
and
see.
in the yeah,
The final
I
product.
make that mistake all the time. Like every single time I use a Wittig, I have to count how many
Yeah.
carbons are in my final product, how many carbons are in my Wittig
hmm
reagent.
Yeah, that's why I think that's why maybe it's useful to draw this positive charge right there, because if you draw it, that reminds you that it's only this portion going in, which is just 1, 2, and 3 carbons, right? And so those would correlate with 1, 2, and 3. So I think not drawing that positive, I think drawing that positive charge has an advantage for this kind of stuff. So yeah, that was definitely an oversight on my part. Yeah, thanks for pointing that out. Okay, so I think that's it for today in terms of review for exam 3. In terms of the schedule going forward, so the quiz is this Tuesday. We will not be able to review the final material before then, but we'll have a meeting on Wednesday and then again on the weekend on Sunday for sure, just like our usual schedule. So for those 2 meetings, we'll go over the final material. If I feel like on Wednesday we're a little overwhelmed in terms of final material, I might add a session on Friday as well. So it would be Wednesday, Friday, and then Sunday, right? So that's the possible situation. But either way, it's definitely going to be Wednesday and Sunday. And definitely do your prep ahead of time because I cannot be available during finals week due to having too many finals. So I can't be available before your actual exam, which I'm assuming is on Tuesday, right?
Monday the 3rd.
Oh my God, Monday. Okay, yes. So I definitely won't be able to do anything to help you guys out there. So Sunday is the last day before your exam. So obviously, please try to be prepared before then and come with all your questions so that we can address that on Sunday. Again, I'm strongly considering adding a Friday session just to make sure that we cover everything. Yeah, and that's it for today.